Hey, good morning, everybody. Yes, what Deb said, this meeting is supposed to be um, on October, but due to the election and got interrupted. And we designed this kind of meeting, to match the times, but now it's all screwed up and it's a month later. Yeah, today's topic is natural air grain drying and storage. The discussion point include self-storage conditions, natural air drying, and we will talk about airflow resistance, equilibrium moisture content, so-called EMC, and we'll discuss some of the drying methods, night-only methods, differential temperature methods, which are recommended by a professor from the University of Regina, and then there's a programming with cable sensors. Uh, Further, we're talking about natural air dry with supplemental heat and some kind of condensation prevention and long-term storage monitoring. On the right side of the slides, I found some of the pictures that old granaries on the prairies. That was a pretty interesting, like about 100 years ago, those are the facility we use to store the grains. And they compared to today's technology, this looks like you know, ancient thing. Anyway, first of all, I want to introduce this kind of storage diagram. And normally this diagram would be, well, they use the moisture content as one assets and temperature on other assets. And the self-storage conditions will be changing with the grain moisture content and the temperature. In general, we all know this as a fact. As the grain moisture decreases, the grain would store for a longer period of time safely and also with the temperature. So this diagram would read like this. This is the line. Divide this part is a self-storage area, and on this side is unsafe. So for each of the crops, the storage conditions are different. This is the barley, and if you look at this diagram, it's slightly different from that. The moisture content goes from one direction to another, and this is when you understand how this range was made, and you could read any kind of diagrams, what it presents, no matter in what format it presents. Yeah, for this particular slide, I show the barley, dry beans, wheat, flax, oats, and peas, and you can see the shape are slightly different, but it's all represent same. Like in the dark purple, represent the unsafe storage conditions, and the green part would show the no spoilage storage conditions. And again, as the moisture content decrease and some in the seed's temperature decrease, the storage time will be longer and safe. Now let's switch to use of natural air for the grain beans. And normally there are three usage. One is aeration. What it is used for is to cool and create an even temperature profile within your storage bin. Airflow rate for these purposes range from 0.1 to 0.25 cubic feet per minute per bushel. And the second use is natural air drying. And at this, for that purposes, to blow the ambient air 5 to 25 degrees with airflow rate from 0.5 to 1.0 cubic feet per minute per bushel through green to reduce the moisture content. That's the purpose, drying to serve drying purposes. And the third one is natural air dry with the supplemental heat. By adding heat to a natural air dry fan to increase the temperature of the intake air going into the storage bin to faster the drying process. First, let's talk about natural air drying. The airflow rate is an important factor as it indicates how much of ambient air that your fan is pushing through the grain and how much moisture this air would take out from your bin as it flow out. And in general, a flow rate of 0.5 to 1.0 cubic feet per minute per bushel is adequate for natural air drying without supplemental heat. And there's one important point I want to emphasize here is turn on the fan immediately after fresh harvested grain is loaded to the bin because at that time the grain temperatures are hot. You turn on the fan not only to remove the moisture from the grain, but also reduce the grain temperature, which is crucial to make the grain safe. If you could drop the grain temperature 10 degrees or 5 degrees, that would make the grain more resistant to the spoilage. And another concept I want to introduce is the airflow resistant. The natural air, the capacity of natural air to dry the grain depends on the air temperature and relative humidity. We all know that like air temperature is lower and the relative humidity is lower, the natural air drying capacity is increased. This is also influenced by the grain type because the different grain have different resistant, airflow resistant. This is a very important measure as it decides how much air can your fan, even at that kind of speed, how much air could push in through your grain. The diagram on the right side show that even at exactly same kind of flow rate, push and see how much of the airflow would go through. And in general, smaller grain like this one is the barley, because the barley is small grain, they packed together, and there's a little voids between the seeds. So when you apply this kind of fan to push through, it got more resistant from this kind of grain. For the pea on the right side, because the pea size is bigger, the air voids between the pea grains are bigger, so it's slightly easier for the air to flow through at the same kind of pressure. So this need to be remembered. In that kind of scenario, the air would flow much easier in the large sized grain beans. The next concept we want to introduce is the equilibrium moisture content, so-called EMC. The EMC represents the moisture content that the grain will eventually equilibrate to if the air condition, to that kind of air condition, remain constant for a length of a period, for a lengthy of time. This diagram, the table over here would show that, for example, at this kind of, if the air temperature ambient air temperature is 10 degrees with relative humidity 60%, and the EMC for the grain is 13.6. That means if you could continuously blow this air and let this kind of air in contact with your grain, and eventually this particular grain would have a moisture content at 13.6%, which is a very important to understand what kind of conditioned air you would use to to dry your grain. Each crop has its own EMC cable, and this particular one is for the wheat. And air EMC is used to estimate how the ambient air condition for grain drying will affect the moisture content of the grain. This is the table I just explained. The EMC and the drying power, the air EMC and drying power, in the nature, it's really hard to find air conditions that stay constant. They never stay constant. They change constantly. So this is a very complicated process, but it really doesn't affect our understanding or our operation to dry the grain. When the goal is to dry the grain, the fan should be on when the EMC is less than the desired final moisture content of the grain. Here's an example. If the goal is to dry the wheat to a moisture content of 14.4%, which is over here, and any EMC numbers that are below this number would have the capacity to dry your grain. For example, 14.3 or 14.2, 14.0. But the drying power would be increasing when the EMC number becomes smaller. You know, if you have the choice and you can, do that to select some kind of conditions on this side to blow through your grain, and that would have a higher power to dry your grain. But any numbers below this 14.4, you should turn on your fans to remove the air. Some very close to this number, like 14.3, 14.2, would less effective compared to those 10, 11, but it's still drying your grain. Dr. Ron Palmer from University of Regina did experiments research on the natural air grain drying for quite a few years at the Indian Head Agriculture Research Farm, and made the following decisions based on his observation done with a few of 2,200 acres of the smaller size beans. And what he recommended is turn the fan on when the yard light is on and shut it off at 9 o'clock the next morning. And this is the first method he feel like it's a simple and easy, no need for any, you don't have to do any calculation or install sensors, just follow this kind of night-day cycles. Because his research showed that, particularly in summertime, when the air temperature in the nighttime, if it's not dropping too much, are very close to daytime, and sometimes the grain is not drying. You blow the air with the moisture in, and the moisture might retain inside the bean, which end up in reweighting your grain instead of drying. So what he said, the fan, using this method, the fan is only on half of the time, so save a lot of energy, which also means the money to you. And it keep Grant the key important message he tried to send to producers is if you could keep the grain colder uh, than continuously fan operation, that make the grain safe as well. So, like a daytime when the outside air temperature is really high, you blow the high temperature into your bean and that warm your grain, which is not a good practice. That's what he's suggesting. The methods itself is not perfect because sometimes it will result fan in running when the outside air conditions are not favorable for drying, particularly for, let's say, if it's a rainy night and the air is warm and the air moisture is really, really high. In that kind of scenario, the second is the differential temperature methods. And this fan is only activated when the grain temperature is higher, for example, 2 to 3 degrees than the outside air. But in this kind of scenario, you would need to have install two temperature, uh, two temperature sensors. One is inside the grain bin, and another one is outside in the ambient air. Because this method always keeps the grain cool, it's more effective in preventing spoilage. So in that case, the earlier example use night only things. If the grain temperature is really is still warmer, still colder than the outside air at nighttime, the fan won't turn on. So these methods can occasionally lead grain to reweighting when the relative humidity of outside air is high. The grain is particularly when the grain is close to dry, that would happen. And the third one is programming with the EMC. And this method requires a calculation of the EMC for the grain inside the bean and outside ambient air. They use temperature and relative humidity sensors to calculate the EMCs. And the fan will be automatically turned on whenever the ambient air EMC is less than the EMC of the grain inside the bean. So if the EMC outside is lower than the inside, the fan is on. This is a much more efficient way in drying grain and avoid reweighting to occur. But the methods require to install the sensor cables to measure the temperature and relative humidity both inside and outside. I guess probably Glenn would give some kind of ideas. I think most of newly installed beans probably should have this kind of sensor cables installed. Another practical suggestion is to level your grain inside bean after you load them. Uh, yeah, because when you use the natural air to blow the air into your grain beans, they they if the grain is not even, I mean the um, depth is not even, the air tend to pass through the lower spots, and less air would go through the higher spots. That would actually lengthy, take a longer time to dry the grain, particularly in those kind of cone areas. So if a grain is left in the cone, or also don't fill the grain too full, and if they have, if the grain have, the air would go through here and expel over here, and very little air would going through this central part to the top, the most thick area, and it would take a lot longer time to dry these beans. Uh, when your grain is, is tough or contain a lot of moisture, speed up drying with supplemental heat is recommended. And this is also happening when the both the grain temperature and the outside ambient air temperature drop below 5 degrees. So the blowing natural air is not efficient in drying your grain anymore. So supplemental heat may become necessary. Warm incoming air will lower its relative humidity, like every 20 degrees, it would increase the would drop would decrease the humidity to 100%. A small amount of heat added may help reach the grain drying goal, warm the air by 5 to 8 degrees, would lower the relative humidity by 20 to 30%. So if temperature increase by 20 degrees, the relative humidity would increase, would be reduced by 100, like 50%. Air, aiming for a planning temperature at 25 but limit air temperature increase by 15 degrees or less, not to add too much temperature into us, too much heat into your incoming temperature. Limit that to 15 or lower or less, somewhere around 10 to 15 degrees. That would, make your drying process efficient and also not to reduce damage the quality of your grain inside the bean, particularly for dry beans. If drying too quickly, and that means if you increase the supplement heat too much, and it would cause crack of seed coat. And when the dry beans seed coat was damaged, and you might see some kind of split beans, and which degrade your bean quality, reduce your selling price. And if too much heat is added, the EMC for the grain is very low, and the grain can be over dried from the bottom part. And drying too quickly can cause damage to the grain, crack the seed coats, and increase risk of a fire as well. And heater selections. And when you install your heater, select only those CSA certified low temperature heater, which are designed for grain drying and storage to maintain a safe and a quality of the grain. An airflow rate between 0.5 to 1.0 cubic feet per minute per bushel can keep up with the moderate drying temperature equipment. And the other, when you increase the heat supplement, add more heat, and you need to have more airflow to take the excess moisture out, which requires the fans, power. With a higher drying rate associated with a higher temperature, particularly in a greater than 30 degrees, ensure a minimum airflow of 1.0 cubic feet per minute bushel to avoid risk of overheat grain. When the heat is supplied, airflow less than 0.5 cubic feet will not enough to remove moisture from the bean and cause grain spoilage. And because you actually heat the grain and the moisture was pushed into a different part of the bean, that causes, problems. Condensation prevention, if the grain is at the center is more than 5 degrees warmer than the grain, as the bean wall moisture may start accumulate near the bean leaves. So particularly in the cold night, and ensure adequate ventilation in the head space in the storage bin is important to prevent condensation. A minimum of 1 square feet of vent space for every 1,000 cubic feet of airflow is required. And in that case, leave enough space on the top of the storage bin would prevent the condensation. So that's another reason you don't load your bin to the top. You can also consider using active ventilation in the headspace to expel moist air. That would be more efficient in drying. And the last slide is to continue monitoring the storage bins. If your grain is stored there for a long period of time, and monitoring of a grain temperature is important. You need to check the temperature inside of your grain bin probably once a month. And if you find that temperature is not even, and you could use the aeration, use the fan for aeration purpose at a low flow rate, for example, 0.1 cubic feet per minute per bushel to keep the grain cool and the profile uniform. Yeah, that's my presentation, and I would let Glenn to talk.
Thank you, Dunlang. Yeah, welcome, Glenn. For those of you that joined late, Glenn Wild is with Top Grade Ag. He has sponsored this meeting today, so Glenn's going to speak to you for about 5 minutes, and then we're going to open it up to questions and comments. And
okay, I sent a request to share, but I think maybe Deb, you have to do something.
Sorry, I think Dunling, maybe if you stop sharing.
Over here. Yeah, okay. Yeah.
Okay.
Oh, sorry for that.
There we go.
Okay. Okay, good morning, everyone. Yeah, my name's Glenn Wilde, and I'm with Top Grade Ag out of Calgary, Alberta. And we aim to help farmers take control of their harvest process. Now, the concept we're introducing is proactive harvest, and there's 3 components to a proactive harvest. The first is to start early and harvest high moisture, top quality product every year. And in order to be able to do that, you have to be able to remove excess moisture using on-farm grain drying. So that's going to be what facilitates our starting early. And the third item is you have to be able to store high moisture grain. So this proactive harvest, there are three goals. Number one, consistent high quality production. So ultimately what we want to be able to enable is farmers put all this effort into growing nutrient rich food. We don't want it laying in the field. We want to capture that quality, and the quality window is extremely small. So we want to be able to help farmers do that. We want to be able to reduce field losses, and we want to be able to, if grain drying occurs, we want it to occur early in the season at the lowest possible cost. Now, the biggest issue that prevents farmers from proactive grain drying is that purpose-built grain dryers are a luxury item, and most farms can't afford them. So what we have done is using bin instrumentation and a web-based app, we basically retrofit existing aeration bins, and we convert them into a purpose-built grain dryer. And what this does is it provides on-farm grain drying to any size farm at an extremely affordable price. This here is some data that we pulled together, and this bright orange is basically it's how many GJs of energy it takes to remove a ton of water. The bright orange is a purpose-built grain dryer, and it's research in the US. And the yellow is also a purpose-built grain dryer in Alberta with PAMI. And you can see that the green, this green is the in-bin drying at PAMI, and the dark green is our Top Grade Ag customers. And you can see that with proper instrumentation and appropriate attention to detail, in-bin drying is very much competitive as far as efficiency goes with any purpose-built grain dryers. So that's a really key takeaway. Now, the other item that is prohibitively expensive is real-time grain monitoring. If you're going to be harvesting high moisture grain, you really need to monitor it probably closer to hourly rather than once a month. And currently, the current technology, if you have, for example, a bin yard with 20 bins, typically it's $1,000 per hardware box to monitor those bins. So 20 bins is $20,000. Now, what Top Grade has done is we've developed a custom box, and we interconnect these bins. So we'll interconnect a row of 10 or 12 bins, and we'll monitor that with one box. And ultimately, that cuts the cost of the remote monitoring down by about 70 to 80%. So you can monitor a row of 12 bins for $1,000 instead of $12,000. Here's a quick look at our dashboard. This is the in-bin drying dashboard. This particular farmer has 4 drying bins. You can see the dashboard shows your airflow rate as soon as your fan starts. And it also shows your heater status. So if you have the heater going, it'll give you your plenum temperature. It also provides hourly updates for the average in-bin, the moisture content of the grain in the bin. It tells you your airflow rate, so how many CFM per bushel. And Dunling mentioned that you want to keep this at 1 or more CFM per bushel. Keeps track of your water removal rates, gallons per hour. And it also tells you when your bin average should reach your target moisture point. We also added a logbook. And that's something that the farmers really like to have. If you have a lot of drying events in bins, you like to look back and see what the results were. In the logbook, you can look and see how much moisture was removed. So you can see here anywhere from 1 to 4 points. The drying duration, how many days did it take? What airflow rate was used? So sometimes with small batches, you have very high airflow rates, and sometimes it's closer to the 1. The water removal rate, so the average, how many gallons per hour were removed during that event, and all the key parameters for the drying events. And then there's a second logbook. This is just a cost report for each drying event, and this is critical for making good business decisions. You can look back on a drying event. You can see the cost that for the fan and the heater. So if no supplemental heat was used, you'd have no heater costs. And then also the total event cost is summarized for every event. And then we calculate a cost per point per bushel. And that's where that really comes into play for helping you make good business decisions. If you're taking something 3 points tough, if it typically we're seeing here, it's anywhere from 1 cent per point to maybe 2.5 cents per point. So if you're taking something 3 points tough, it's going to cost you roughly 7.5 cents a bushel. And again, this particular customer has a natural gas supplemental heater, so that has to be kind of taken into account. And then we also provide you with how much heat was added per hour, so how many BTUs per hour. So that helps you understand what size heater you need for your drying bin. And then this is the last part of our dashboard. This is the actual grain monitoring. So we read any 2-pin OPI compatible temp cables. This is each line is a bin. You can see all the temperatures and you can see where the grain is. This is an example of a 7-day graph for a bin that is got nice stable grain. It's not heating up. You can see these sensors are up in the air, so they're going up with the air temperature. Here is an example of a bin where the wheat actually was warming up and it triggered the alarm. And here is what the farmer found when he moved the grain. But you'll notice that this alarm was set at only about 17 degrees C. So almost no waste was experienced. And anyways, that is a real quick rundown of Top Grade Ag and what we are, I guess, trying to provide. If there are any questions.
Great. Great. Thanks so much, Glenn. And sorry, I was pronouncing your last name wrong there. So
Oh, no worries.
Awesome. Well, thank you so much. So I'm going to stop recording now.